Okay, so now after determining the order of a reaction or order with respect to specific reactants, the integrated rate law is our next step in determining some important aspects of kinetics. For a reaction where we have one reactant, A, going to products, the rate law depends on the concentration of A. Applying calculus to integrate the rate law and to give another equation, we actually can show the relationship between that concentration of A and the time of the reaction. So anytime we want to integrate time into our rate law, we are looking at the integrated rate law. For first order reactions, okay, so this was looking at rate equals the rate constant K times the concentration of A to the first power. Again, this is just for a very simple reactant A goes to some old fan-dangled products. Again, we don't care about the products. This is kinetics. The rate law can be integrated, and that integration results in this. The ln of A at time t is equal to the negative K times T plus ln of A initial, all right? This is the initial concentration of A. This is concentration of A at a time equals whatever you want it to be. That is the same time, right? And K, again, is the rate constant. Now, ln, the natural log factor, right? So that is a mathematical operation to integrate time into our specific rate law. It's not a minus sign. This is just like a bullet. So just make sure you note that. The graph of the first order can be determined by plotting time on the x-axis and ln of A on the y-axis. The intercept at time t will be the initial concentration, the ln of the initial concentration, and a straight slope will be generated. The slope of that graph is negative K. Now, how do we know this? Well, if we look at the actual equation, the integrated rate law, we see that it follows the same y equals mx plus b format, all right? So remember, when we graph a line, y equals mx plus b. The y-axis is the ln of A. M is the slope, which we have determined is negative K. X is the x-axis, which is time. And plus B is that y-intercept right there at time 0. What's the initial concentration? With this, what we can actually calculate is a half-life. A half-life specifically is the time at which half of A has reacted. All right, that is the definition of your half-life. A half-life for a first order reaction is constant. The equation is time 1/2, that is the abbreviation for half-life, is equal to 0.693 divided by K. Essentially, what we're taking is we're taking this equation and we're saying, when will the initial concentration be halved? If we started with an ln of 1, right? Say we start with initial concentration of 1, at what point will that reaction have a concentration of A at 0.5, half of that, okay? If we rearranged these, that's where we would start to see what comes up of 0.693 divided by K, okay? How do we get there? the ln of 0.5 is negative 0.693 equals negative k times the half-life plus 0. Ln of 1 is 0. So then we just divide both sides by k and minus 1. And that's where we get our half-life is equal to 0.693 over k. All right, the negatives cancel and k will be in the denominator. For second order reactions, remember this is the rate. Rate is equal to k times the concentration of reactant A squared. The integrated rate law shows up to be 1 over A at times T is equal to KT plus 1/2 or 1 over A initial. Now again, this would result in a straight line. If we plotted the data with this setup, then we would see a straight line graph. And the same type of y equals mx plus b format. I'm going to write it over here. 1 over the concentration of A at times T is equal to KT plus 1 over concentration initial. Y equals mx plus b. Y, we plot 1 over A at times T. The slope is a positive K. X, we plot time T. And different color. B, the y-intercept is 1 over A initial. All right. Again, the half-life can be derived. The half-life for this, when we plug in A initial is 1 and A at times T is half of that, 0.5, we would get a half-life of 1 over K times the initial concentration. So the half-life for a second order reaction is dependent on the initial concentration. All right. Zero order reactions. These ones are tricky because when we think about no dependency, we still have an integrated rate law, okay? So again, for rate is equal to k times a to the 0 power, which would just be equal to k, what we see for our integrated rate law is the concentration of A at time t is equal to negative KT plus A initial. Even though this is a zero order reaction, that means the rate itself, how fast or how slow something goes, is not dependent on the actual initial concentration of our reactant. But that doesn't mean that we don't need that reactant. That reactant is still important, right? The concentration still needs to be there. If we didn't have any A in our sample mixture, we wouldn't make products. So it still needs to be there. It just can be 1, 2, 3, 4, whatever it needs to be. It doesn't depend, the rate itself doesn't depend on that concentration. So again, just to see what do we plot, the straight line would form for a zero order reaction when we plot Y is concentration of A at a specific time. M, the slope, again, a negative K. X, on the x-axis is time t, right? And plus B. The y-intercept is, again, A initial, all right? So constructing a graph of concentration versus time results in the straight line. And the half-life is going to be, again, dependent on the initial concentration divided by 2K. Overall rate loss summary table. This is a great table just to be able to look at and to start thinking about the integrated rate laws for each of the rate law expressions. You do need to know the integrated rate laws. I try to provide them everywhere I can so that we can start using them and really understanding them. You shouldn't need to derive those integrated rate laws yourself, but you should be able to be familiar with them. Notice your book writes the integrated rate law for a first order reaction one of two ways. Either way is appropriate. The first one listed there above is written in y equals mx plus b format. The second one is more of a condensed, easier to input into your calculator format. Let's talk a little bit about just half-life again. There are many types of ways to calculate this half-life idea, but a half-life by definition is going to be any reaction, or the half-life of any reaction is the length of time it takes for the concentration of reactants to fall to 1/2 of its initial value. The half-life of a reaction depends on the order of the reaction. So we see, especially in that previous chart in table 14.2 in your textbook, that each order, 0, first or second order, has a different calculation for half-life. But you can have multiple half-lives. All right, so if we start at a concentration of 1 for a specific reactant, once it reaches half, that's the first half-life, right? When it gets to a concentration of 0.5. Then we could have a second half-life when it gets to 0.25, a third half-life when it gets to 0.125, et cetera, okay? So there are multiple ways or multiple times you can calculate that half-life. The relationship between order and half-life is very important. Essentially, to figure out or to derive the half-lives for each order, we would take the integrated rate law and plug in A initial is 1, and A at time t would be half of that, 0.5. You could choose any two values that you wanted to derive the half-life, as long as the initial was twice as much as the A at times t.